We're going to start digging deeper into the relationship between risk and return. In the previous videos, we've generally said that there's a connection there. If you take on more risk, you should expect more return. In this section, we'll get into how to measure risk and return and how investors are compensated for taking on that risk. We'll start with the return side. A return, or rate of return, is simply what you're earning on an investment over some period of time. It's a measure of an investment's performance. This includes all aspects of earning, the total return. If you receive a dividend check, that will be included in your return over that period. If the price of the investment increase, that will be a part of the return as well. We can express the total return of an investment with this formula that should look pretty familiar. The total return is the change in price over the period, that's P1 minus P0, plus the cash flow earned over that period, CF1, all over the current price, P0. We can separate this formula into two components. First, the price or capital gains component. The capital gains yield will illustrate how much the investment has changed in value over some period of time. And the income yield will illustrate how much cash flow you earn from the investment. We gave this different names depending on the type of the security we're looking at. For bonds, we call this the current yield, and for stocks, we call this the dividend yield. Let's do an example to compute a return ourselves. Let's say at the end of 2018, Starlight stock had a price of $150. And 1 year later, at the end of 2019, it had a price of $175. In addition, the stock paid out a dividend of $5 over the year. And we want to know what the return on this investment was. Putting our information into the formula, we get a result of 20%. Considering both the stock's change in value and the income we received over the year, this stock provided us a 20% rate of return. The return we just computed looks at the investment's performance over one period of time. But what if we wanted a summary of how it performed over a wider range of time? We could then compute an average return. We'll discuss two different types of averages here. The first is one you're probably very familiar with. It's called the arithmetic average. And it's just a simple average. Imagine trying to compute the average height of students in the classroom. How would you do it? You would ask everybody their height, add all those numbers up, and then divide by the total number of students. Well, it's exactly what we're going to do here with the arithmetic average return. To find this average return, you'll observe the returns on an investment over some period of time. Those are going to be our observations. And you'll divide by the total number of observations. This average represents what we could expect as a return in a typical year. If you took all the observations, put them in a hat, then picked one out at random, this is what we could expect to pull out. A slightly different measure of average returns is called the geometric average. This average is going to measure the compound growth rate on an investment over a period of time. Notice that I said compound growth rate. This average takes into account the fact that money compounds. Money you earn in prior periods will grow in future periods. So this average will tell us the effective rate of return. On average, how much did we actually earn over a period of time? We can do an example to show how these two different average measurements have different interpretations. Suppose you put some money in the stock market and earned the following returns over 5 years. 90%, then 10%, then negative 100%, then 30%, and finally 20%. Let's find out both the arithmetic and geometric average returns here. First, arithmetic. This will just be a simple average. We'll take all 5 observations, sum them together, and divide by 5. And we get 10% as an arithmetic average. Again, the interpretation of this type of average is, if I picked a year out at random, what can I expect that return to be? With this data, I could expect the return to be 10%. For the geometric average, we want to apply this formula here. It's the fifth root of all the stuff under that root symbol, minus 1. It can be kind of difficult to compute this fifth root, so we can rewrite it like this. We'll just raise all the stuff in the brackets here to the 1/5 power. That gives us the same result. And the result I get is negative 100%. This is the geometric average return. Now let's interpret this. Imagine you invested $100 in the stock market over these years. If you had a 90% return the first year, your $100 would grow to $190 after 1 year. With the 10% return the following year, the $190 will grow to $209. But in the third year, you have a negative 100% return. What does it mean to have a negative 100% return? that just means you lose everything. So the $209 that we had falls to $0. And the next year we have nothing. So even though the stock market gave us a 30% return, there's nothing invested. So we end the year with $0. And the same story for the final year. So what did our $100 investment grow to over 5 years? It grew to $0. So effectively, we had a negative 100% return on investment. And that corresponds to the geometric average we computed. We just computed average returns, which deals with historical data and looks at what happened in the past. But we can also compute expected returns, which will look at what we expect to happen in the future. For this, we need to have some forecast of the outcomes we expect to see in the future and the probabilities with which we expect those outcomes to occur. The expected return will be the weighted average of the future outcomes, with the weights being the probabilities. Let's do an example to see how all this works. Suppose you forecast the economy to be in one of three conditions in the future. We either will have a booming economy, a normal economy, or we'll be in a recession. We forecast that there's a 30% chance we'll be booming, and the return on investment if we are booming will be 25%. There's a 60% chance of being normal, and that comes with a 10% return. And finally, there's a 10% chance we end up in a recession, and that comes with a negative 5% return. To get the expected return, we need to weight the outcomes in the future by the probability of those occurrences. There's a 30% chance of getting a 25% return, so 30% times 25% is 7.5%. There's a 60% chance of getting a 10% return. 60% times 10% is 6%. And lastly, there's a 10% chance of getting a negative 5% return. 10% times negative 5% is negative 0.5%. Notice that the probabilities will sum up to 100% because one of these three outcomes must occur in the future. There's a 100% chance we'll end up in one of these three states. Summing up the probability weighted outcomes in the final column gives us 13%. That's the expected return. Given these forecasts, we can expect a 13% rate of return on investment. Now that we spent some time talking about returns, it's now time to discuss the other side of the equation, risk. The word risk represents uncertainty. If you don't know for certain what the outcome of something will be, then you're taking a risk. Going skydiving is a risk. Placing a bet at a casino is a risk. Flipping a coin, it's a risk. The word risk usually has a negative connotation, but it's important to note that risk isn't necessarily a bad thing. There's both upside risk and downside risk. In the stock market, for example, the future is uncertain, but that uncertainty may work out in your favor. That would be upside risk. But there's also a chance it can work against you, and that's going to be the downside. We can look at these two stocks and get a feel for what we mean by riskiness. Stock A is like a roller coaster. Some months its return is very high, other months it's very low. So it has a lot of risk. Imagine trying to forecast what's going to happen in month 14 for the stock. It'd be pretty difficult to do so. Contrast with stock B at the bottom here. Its return is fairly stable. Yes, it fluctuates, but for the most part, the return stays in a pretty narrow range. So relative to stock A, stock B is less risky. If we had to forecast the return in month 14 for stock B, we'd probably have a better chance of being correct. Now let's quantify risk. We can measure risk using standard deviation. Standard deviation will tell us how much volatility or fluctuation there is. It gives us an indication of how much uncertainty we have. It says how far away are the outcomes from what we expect. We can measure standard deviation using historical data by computing the historical standard deviation. Or we can use expectations about the future to compute expected standard deviation. These formulas here may look a little daunting to you, but I'll go step by step to show how they're implemented. Let's first compute historical standard deviation. Let's say there's a stock that has returns of 20%, 30%, 5%, negative 10%, and 2% over the past 5 years. And I want to know, what is this stock's standard deviation? The first step is to compute the arithmetic average. We're going to use this to represent the expected return. Computing this average, we get 9.4%. So if we had to guess what the return next year will be, 9.4% would be a reasonable estimate. Next, we need to find out how far each of these observations were from that average. So we'll take the observed return and subtract it from the average. We'll call this result the deviation from the average return. Our next step will be to square those deviations. This is done to treat positive deviations the same as we treat negative deviations. Next, we'll need to add up all those squared deviations, and finally apply the formula, where we have the square root of the sum of squared deviations divided by the number of observations n minus 1. And we get 15.7%. This means, on average, the returns we observed are 15.7% away from the average, or what's expected. A bigger standard deviation represents more risk or more uncertainty. We can go back to our two pictures from earlier and quantify the risk that we visualized with standard deviations. Stock A has a standard deviation of 25.2%, and stock B has a standard deviation of 3.8%. As we can see, the more volatile the movements are, the greater the standard deviation. So that was historical standard deviation. Now let's get into computing expected standard deviation. The process is nearly the same, except this time we need to deal with our expectations and their probabilities, rather than actual observations. We'll use an example from earlier with the 3 possible economies in the future. Our first step will be to compute the expected return, which we did previously and got 13%. Next, we need to find out how far away each of those economy returns are from what is expected. So we're going to compute the deviation from expected return, as the 25% return we get in a booming economy minus the 13% expected return. Then the 10% return we get in the normal economy minus the 13% expected return. And lastly, the negative 5% we get in the recession minus the 13% expected return. Next, we'll square each of those deviations from the expected return. So 12% squared, negative 3% squared, and negative 18% squared. After that, we'll weight each of these squared deviations by the probability of being in that type of economy. So 30% chance of being in a booming economy times 0.0144 squared deviation, and do the same for all states of the economy. Add those together and we get 0.00810. Finally, taking the square root of that gives us 9%. That's the expected standard deviation. The last thing I want to cover here is the concept of coefficient of variation. Its usefulness is best described with an example. Imagine trying to choose between 2 investments, Hydrogen Corp and Nitrogen Corp, and your objective is to maximize return while minimizing risk. Which of these 2 should you choose? Looking at the statistics, there's not a clear choice. Nitrogen has a higher expected return, so it's better in that dimension, but it also has more risk, so it's worse in that regard. So how can we make this comparison work? Well, we can turn this information into a ratio and look at the amount of risk we're exposed to per unit of return, a risk to reward ratio. That's going to be the coefficient of variation. The coefficient of variation is the standard deviation divided by the expected return. That's going to give us risk per unit of return. Computing the coefficient of variation for these 2 companies, we get 1.2 for hydrogen and 1.33 for nitrogen. And we can interpret this as saying for hydrogen, we're taking on 1.2 units of risk for every unit of return. While nitrogen, we're taking on 1.3 units of risk for every unit of return. So if our objective is to maximize return while minimizing risk, we should invest in hydrogen. It gives us the best trade-off there.